Okay, so picking up homework 6-5 here, we were on question 4. Really, we had set it most of the way up, so hopefully you guys were able to kind of finish it from here. But obviously, if you do want to check your answer, I'll go ahead and work it the rest of the way out. I will try to be pretty quick with it, though, so you can check. All right, so again, solving this for the final velocity, that's what we're looking for. So really, I have two of these, and then I add them over to the other side. So I'm going to write that as 2g m2 all over r. And because then I know, right, both of the masses, I know the mass of each of the stars, and I know the distance to each of the stars. Right, so hopefully this question's now pretty easy to solve. So 1/2 the final velocity squared equals 6.67 times 10 to the negative 11th, right, for our universal constant. The mass of each of the stars is 1.99 times 10 to the 30th. And then again, the separation from each star individually, I do not use the total 1 times 10 to the 12th, I just use 0.5 times 10 to the 12th. Right, so solving that out, and then solving for v, right, so I'll trust that you guys can do the mathematics here, but I end up getting about 32,586, right? So obviously you can round that off where you feel appropriate here, but I'll go ahead and write it out a couple of significant digits there. So the final velocity, the final speed should end up being 32,586 meters per second. So again, the key on this question here is making sure you're comfortable with the fact that as I look through, right, it starts infinitely far away, so it starts with 0 joules of total energy. As it gets closer, it is, however, right, losing potential energy because it's becoming more negative potential energy. And if it's losing potential energy, that energy has to go somewhere, and that's going to kinetic energy, which obviously then it's gaining. And so that helps me find the velocity. Right, so a couple tricks to question 4, probably one of the 2 or 3 more difficult questions on this homework. Questions 4, 6, and 7, I think personally, are probably the trickiest questions on this homework. But anyway, we'll look at question 5 here, and then we may need part 3 to get through questions 6 and 7. So anyway, let's get through question 5 for sure here, and we definitely will have enough time for that one. But this is another one that, like I said, hopefully not too bad. It does take advantage of energy conservation here, and obviously it takes advantage of this being an elliptical path, which we'll see as well. But actually for part A, I think there's probably enough information to where we don't even necessarily have to worry about it being an elliptical path, right? They tell us that Pluto has an elliptical orbit, Pluto's speed at the closest approach, so they give us the distance and the speed at that closest approach, and then they ask us what is the speed at the most distant point in the orbit, which is obviously this distance then away from the sun. And so again, for part A, even though you could set up the ellipse and think about the motion, which I will do to help us kind of solve part B, for part A, really, as soon as I recognize that, because I've got my distance and I've got my speed, right, it's just an energy conservation problem. I know that the energy is conserved throughout the orbit, whether it's a circle or an ellipse, energy is conserved. So the kinetic energy plus the potential energy at some point in the orbit needs to be equal to the kinetic energy and the potential energy at really any other point, right, in that orbital path. So since they give me really pieces to 3 of the 4 here, hopefully we can then find the 4th and final missing piece, right, to find our speed at that most distant point. So let's go ahead and plug in and see if we do have enough information, right? So breaking this up, again, 1/2 mass times velocity squared minus g m1 m2 all over r, as we've seen a number of times now. And then over here, 1/2 mass times, I'll go ahead and call this velocity 2 just to distinguish that. That is going to be the velocity that we look for here in a moment. And then again, minus g m1 m2. And similarly, I'll go ahead and call this r2. Maybe throw some 1s over here just so we don't confuse those, right? But anyway, this is the setup we've got so far, right? If I look through each of these terms, what does each term have in common? Well, each term has the mass of the satellite, right? m1, if you will, that comes into play. So if I were to take this equation right now and divide everything by m1, I could just get rid of it, right? I'm just dividing each term by m1, so it's gone. So then from here, again, they've given us so many pieces that hopefully this isn't a terribly difficult problem. I've got 1/2. They do give me the initial velocity. Keep in mind it is in kilometers per second, so I'm going to go ahead and convert that to meters per second. I'm going to make that 6,120 meters per second squared. And then minus 6.67 times 10 to the negative 11th. What mass would I need here? Well, again, this problem, I didn't give you the mass in here, but I do expect that you would realize that, hey, I need the mass of the sun, right? That's what I'm orbiting around. And once again, if you look at one of the previous problems, the mass of the sun is in there for us. So we've got that to work with. We just need to use it. So the mass of the sun, 1.99 times 10 to the 30th. And then the closest radius, right, the radius at which it's moving, 6,120 meters per second, is 4.43 times 10 to the 9th kilometers. But again, keep in mind, watch our units there, right? So that would actually be 4.43 times 10 to the 12th meters. So I do want to make sure I put that in standard units. Over here, then, I've got 1/2 the final velocity, or the second velocity, which is what I'm looking for, right? That's going to end up being my only variable. And then 6.67 times 10 to the negative 11th, times, once again, the mass of the sun, 1.99 times 10 to the 30th, all over the radius to the furthest distance, right? And so that's the 7.30, again, times 10 to the 12th, once I convert that to meters, right? They gave us 10 to the 9th kilometers, but when we multiply that by 1,000, that adds 3 there, so 10 to the 12th meters. But anyway, again, as soon as you set this up, I'm confident you guys would be able to say, okay, I've got everything I need except that velocity at that second position, right? So finding the velocity is as easy as just making sure we're careful with our computations. And again, hopefully I know it is possible that I make a mistake as I go through here, but I am pretty confident that this is the correct answer. So check me on that, let me know if you disagree, but I do believe that our final velocity at that second location, and notice I went ahead and wrote it again in kilometers per second, but 3.73 kilometers per second, or 3,730 meters per second, right? That ends up being that final velocity. It does make sense. It does seem like a reasonable measurement to me, right? And the reason I say that is originally we were moving at 6.12 kilometers per second, but that's when we were closer, right? That's when we were closer to the sun. As we get further away, the potential energy is going to increase because it's going to get less negative. So doesn't that mean the kinetic energy and therefore the velocity should decrease, right? So I know that's not necessarily relevant for this question, but it is a piece of advice I would always say when taking a test is just stop and make sure that seems like a reasonable measurement, right? It seems very logical that the velocity would go down because the potential energy should have gone up, right? So anyway, that's enough harping on that for right now. Part B, what is the period of Pluto's orbit around the sun? And the key, obviously, this question here, the key concept is making sure we're comfortable with the fact that I'm finding the orbital period for an elliptical path. So when I'm finding the orbital period for the elliptical path, right, I can't just use the equation that we've seen a few times before, right? I can't just do this where I have r, because the radius isn't uniform. So I'm not able to just use this equation that we've seen from Kepler's third law. Instead, the only change that we have to make if it's an ellipse, right, if I want to find the period, if I want to use a relationship for the period, it's almost exactly the same, except we substitute, instead of the radius, we use the semi-major axis, right? We use half of the major axis, which is represented by an A. So really the only key to this question becomes, can I find A? Because once again, I know the universal constant, I know the mass of the sun, and then I've got obviously 4 and pi, which are just constants. So if I want to find the period, I've got to find A. And this is a question that if you've done homework 1, you've done a few times now already, right? So obviously my ellipses are not very good, but this will work well enough for what I need. So we know the ellipse, we know that the sun would be at one of the 2 foci locations for the ellipse. And then if I'm interpreting the information, it tells me the closest path that Pluto reaches is at certain distance of 4.43 times 10 to the 9th. So they give me this measurement, 4.43 times 10 to the 9th. And then I know the furthest location, which I have to conceptually realize would be the other end of the ellipse, right? It'd be all the way to the other vertex over here, right? They give me that distance, that radius is 7.30 times 10 to the 9th kilometers. And keep in mind, these are both kilometers and not meters. But anyway, the significance there is together, collectively, those 2 would make up my major axis, right? Together, those 2 would make up my major axis. And the key concept is the major axis is 2a, which is twice my semi-major axis, right? Which is twice the measurement I need. So really, the relationship we take advantage of, and again, you guys have hopefully done this a few times already, but 2a would equal just the sum of those 2. So 4.43 times, I'm going to go ahead and convert this back to meters, so 10 to the 12th meters, plus 7.30 times 10 to the 12th meters. So really A is just obviously then going to be half of that measurement, right? I divide both sides by 2 and go from there. So calculating for A, obviously it's going to be midway between those two. And in fact, when I solved for A, I believe I get 5.865 times 10 to the 12th. So now that I've got my A in terms of, I've got my semi-major axis in terms of meters, in order to find the period, it is just a matter of taking that and plugging that in, right, substituting that in up here into my relationship for the period, right? So again, t squared equals 4 pi squared times this whole quantity, and obviously just be careful as you calculate this, whether you're using the E button in your calculator or using just parentheses like a madman, right, which might be the best approach. I don't know, whichever the easiest for you. But as we're plugging this in, just make sure we are very careful, right? We need to do this whole quantity all to the third power, and then that whole thing divided by both 6.67 times 10 to the negative 11th, and the mass of the sun, again, 1.99 times 10 to the 30th, right? So again, as we calculate this, that would be t squared, and then as I obviously square root that, I end up getting a period of 7.75 times 10 to the 9th seconds. Now, this particular question did not ask us to answer in terms of years, so I'm actually going to go ahead and leave it as that. Obviously, if you wanted to convert this to years, you just need to figure out how many seconds are in an Earth's year, and then divide this quantity by that number. But in this case, even though maybe not quite as practical, I am going to go ahead and leave that just in terms of seconds. Anyway, hopefully question 5 wasn't too bad. Like I said, if you've done homework 1, if you feel pretty confident on homework, and I say homework 1, but I mean homework 6-4. But if you've done pretty well with that one, I think you guys will agree, maybe not too bad with question 5. Questions 6 and 7 are both very, very tricky. So I do think I'm going to go ahead and work those. I'll try and work both those in part 3. But both of those are ones that I expect us to maybe have a little bit of trouble with. So I would strongly encourage you guys to obviously try those first, look through them, but then make sure you do kind of look through the videos and let me know if you have questions once you get to those. But anyway, I will do homework questions 6 and 7 in part 3 of this video.